In this video, we will prove whether the following problem is decidable or undecidable. The problem is LOOPTM, and it's defined as, given a Turing machine M and a string W, does M loop forever on input W? So we are going to define a language, LOOPTM, and it's going to be the set of strings M, W, such that M is a TM and M loops. Remember, looping is the same thing as running forever. If we see the same configuration twice, we're looping on string W. Okay, so this is our language and we're trying to decide, is it decidable or undecidable? So our claim is going to be that LOOPTM is undecidable. Okay, so our idea is going to be to reduce ATM to LOOPTM. Okay, so how are we going to do this? So if we think about what a Turing machine does on a string W, the Turing machine is going to do one of three things. Okay, either one, it's going to accept. Two, it could reject, enter the reject state and halt. Or three, it could loop, which is the same thing as running forever. Okay? So notice that we can make any machine run forever. Okay, so any machine can be made to run forever. Okay, what does this look like? Well, we could move past the end of the input and enter a sequence of states where the tape head moves to the right and then to the left and then to the right and to the left. So this would be looping forever. So let's just imagine that the machine does something and then it enters this set of states where we read a blank and we write a blank and move right. So we need to be past the end of the tape to do this. We could do it in other ways, but this is just showing you that there is at least one way to do this. And then after moving to that state, we could read a blank, write a blank, and move left. So if this is my tape, and maybe this was my end of my input, if I can move the tape head, say here, then I could write a blank and move right. And then I write a blank and I move left. And I write a blank and I move right. Okay, so all it's ever going to see is a blank, so it's going to keep taking these transitions and it's just going to move left, right, and run forever. Okay, so our idea is going to be we want to combine 2 and 3. We want to collapse these options, okay, or these outcomes. So what we want to do is we want to modify a machine that when it rejects, it enters a reject state. Instead, it enters a sequence of states that cause it to run forever. Okay? So that's going to be our idea. Our idea is going to be to collapse rejecting and looping into one outcome. Okay, so if this machine were to reject, instead we're going to make it run forever. Okay, so given this idea, what we're going to do is, if we have a decider, let's call it D, for LOOPTM, if our modified machine, how do I want to say this, M prime, along with string W is accepted by LOOPTM, then M prime does not accept W. Okay? So we take the machine, and if it rejects, we make it loop forever. And if it loops forever, it's already going to loop forever. Okay? So if this modified machine, M prime, and the input string W, if this input is accepted by LOOPTM, then we know that that machine did not accept W. And likewise, M does not accept W. Okay, M was our original machine. And if M prime W is accepted by LOOPTM, then either M rejected W or M ran forever on W. But either way, M didn't accept W. Okay? And if, I'm just going to, M prime W is rejected by LOOPTM. Why is this? It's because M prime W looped for, or did not loop forever on W. That means that M prime accepted W, which also gives us that M, our original machine, accepted W. This is because we're only collapsing, rejecting, and looping forever. We're collapsing those into one outcome. So we're not affecting what happens when the original machine actually accepts W. That's always going to, M prime is always going to accept W if M accepted W. Okay? So hopefully you can see how we can use this decider, D for LOOPTM, to decide ATM. Remember, ATM is the set of strings MW such that M accepts W. So this is what we're interested in. We're interested in deciding when M accepts W. Okay? So let's show our proof. So let's suppose LOOPTM is decidable and its decider TM is D. Okay, so how do we reduce this to ATM? We are going to construct a decider, let's call it A, for ATM as follows. What does A do? Remember, it's a decider for ATM, so on input it needs to take a machine description and a string. The first thing it's going to do is create a new TM. I'm going to call it M prime from the description of M. But we're going to modify it. So replace transitions that would enter the reject state of M. And we're going to do this replacement in M prime so that M prime loops on W if M rejects W. Okay, this is the modification we were talking about, and this is possible to do. I showed you a quick example of some way that you could make a machine run forever. Okay, so what we're going to do is whenever M would enter its reject state, M prime is going to enter this sequence of states so that M prime loops on W. Okay, so we have our new TM M prime that's basically M except for this change where it's going to loop if M rejected. And then step 2, we're going to run D, our decider for LOOPTM, on the description of our modified machine and our original string W. Okay, and what are we going to do with its response? And we're going to reject if D accepts, and accept if D rejects. Okay, we're going to do the opposite of whatever D did on M prime W. Okay, so let's convince ourselves that this actually becomes a decider for ATM. Let's check what happens. So if we're given an input MW and it's the case that M accepts W, then what would happen? Then M would enter an accept state and halt. Okay, so because it halts, and on W. Okay, remember that our modification doesn't change the behavior when M accepts W. It only changes the behavior when M rejects W. Okay, therefore M prime, how do I want to say this? Enters an accept state and halts on W. Okay, therefore M prime does not loop on W. Okay, since it doesn't loop, it means that this M prime W is not in LOOPTM. Okay, because it's not in LOOPTM, D rejects M prime W. Okay, which means our decider A for ATM accepts the original input MW. Okay, so we have that if M accepts W, then A accepts MW. So it's looking good so far. Let's see what happens if M does not accept W. Okay, we kind of have two cases to worry about. So if M doesn't accept W, then M rejects or loops on W. Okay, so if, let's say if M rejects W, then M prime loops on W. And I'm also going to say that if M loops on W, then M prime loops on W. Okay, and here I'm going to bring them back into the same argument. Okay, so because M prime loops on W, this means that M prime W is going to be in the language LOOPTM. Okay, we had a decider for that. It's called D. So D is going to accept M prime W. And remember, our decider A for ATM does the opposite. So A rejects the original input MW. Okay, so we have if M does not accept W, then A, the decider for ATM, does not accept MW. It rejects MW. Okay, so we have that A is a decider for ATM, which is a contradiction. Okay, and let's go back. So where was our claim that we didn't have any facts to prove? It was that LOOPTM was decidable, which gave us the decider. Okay, so we have a contradiction because this claim is not true. So then we have that LOOPTM is not decidable, and therefore it's undecidable. And that's the end of our proof.